So I will be presenting some joint works that I did with Yevgeny, who is co-organizing this day, and with a CNRS researcher at Orsay. It's also a joint work with Vincent Divol, who is now an assistant professor at NSAE, and with Nicolas Schroeder, who is also a CNRS researcher at Université Gustave Eiffel. And this would be the second part of my talk, because I was asked by Yevgeny to give an introduction to some topics in fairness, and actually it's a good opportunity to give you a broad view before diving into a very specific problem that we tackled. So I guess I don't have to convince you that machine learning is everywhere, but maybe from the lab from our lab we have a biased perspective on what its applications are. So here is the point of view of the journals for. AI is used for a wide range of applications, from predicting where crime will happen in advance in order to dispatch police forces, to helping in recruitment processes, to pre-select a few resumes in order to decide to whom to grant an interview. It's used to help with medical diagnosis, but actually also during drug design. It's used to grant loans and you may have heard also about the Hollywood writers' strike last year, and the Hollywood writer the scenarists had fears about losing their work and being replaced by AI. It was used. It's used for facial recognition, and it has been used during the Olympic Games for that, etc. And so, just by a show of hands, how many of you have already seen a presentation on AI, problems of fairness in AI? Okay, so quite a lot of people, and I guess you have already heard about some of the problems and examples of biases in AI, and most likely you've already heard about the article in the middle. So it's an article that was written by journalists working for ProPublica, the one titled Machine Bias. And they investigated a software used to assess the likelihood that criminals would become recidivists. And they found that, well, first, the predictions were really not accurate. When taking lots of crimes into consideration, and also petty crimes, it was barely more accurate than a coin flip. But also they found that the predictions were racially biased, in the sense that if you were an Afro-American and you did not become a recidivist, you are still labeled as presenting a high risk with twice the race as if you were Caucasian. So this article really raised the awareness of the community, and people have been looking at problems of bias in AI ever since. And they found that actually biases and discriminations are pervasive. For example, so the text is really blurry on the right, but you can run an example to test for the biases of ChatGPT, and if you asked it to analyze a sentence, the doctor yelled at the nurse because she was late, and asked it who is late in this sentence. Could be the doctor or the nurse, because jobs are gender neutral in English. ChatGPT tells you that when I say the doctor yelled at the nurse because she was late, she is the nurse. But if I reverse the order and say the doctor yelled at the nurse because he was late, he is still the doctor, and I can ask for the nurse yelled at the doctor, and you would consistently get that she is a nurse, he is a doctor. And if you ask Copilot to illustrate what is happening with doctors and nurses talking, nurses are always women, doctors are always men, and, well, they are both Caucasian and young and good-looking. So you really have what is called representation bias. And there have been many other examples, just to name a few. Well, I was discussing the use of algorithms to predict where crime will happen. It has been shown that these algorithms tend to predict crime in districts that are, where the majority of inhabitants belong to certain ethnic groups. I told you about using AI in recruitment processes, where Amazon was developing a tool to select resumes for hiring engineers, and they had to give it up because it was systematically discriminating against women. But that's not the only problem in the recruitment process, because Google algorithm is also showing ads for prestigious, high-paying jobs more often to men than to women. And there have been other examples of, for example, bias in the AI tools used to detect benefit fraud. So here the example is in the UK, but last year we had a similar article by Le Monde saying that the CAF algorithm was targeting the more fragile households. There have been biases in facial recognition, in the way Twitter was cropping images to focus more and more on certain persons or others. And, and there have been many other examples. So why are there biases in machine learning algorithm? Well, this is a very schematic way of how a supervised learning algorithm works, but basically you give them labeled example, you use your favorite supervised learning algorithm to obtain a model. And this model, now we should give it a new piece of information, will make a prediction by replicating the relationship that it has learned from the data. And especially if this data contain biases, this machine learning algorithm will replicate the biases, the stereotypes, the discrimination that is historically present in the data. So, and there are multiple causes for bias in the training data. The most obvious one is simply you have an unbalanced data set. For example, you're Amazon and trying to learn how to recruit people, but historically you've recruited very few women, so you're going to be very inaccurate for these people. And sometimes the fact that you have unbalanced data sets can be historical or can be due to the way you measure and you obtain your data. For example, if you want to predict crime, you often don't have access to crime-based data, you have access to arrests. And well, you know that police arrests are racially biased. In some cases, you are simply trying to automate a task that was previously done by the human, so teach the algorithm how to reproduce the human way of making decisions. And if you're automating, for example, what a human recruiter would have done, but this human recruiter had biases that could be racist or sexist or whatever, you're going to reproduce these biases because reproducing the decisions. There are other causes. One is a bit more subtle. Sometimes you want to predict something, but you don't really have access to the quantity you want to predict, so you use a proxy that is, a good proxy for the task you're predicting, but is a biased one. Again, if you want to predict crime and you use arrests as a proxy, this is a good proxy. You can approximate that most of people who commit crime will be arrested and most of people who have been arrested have committed a crime, but it's also racially biased. It's not an unbiased proxy. So this is why we have bias in the data. And the thing is, machine learning algorithm does not simply replicate biases. In some cases, these biases can be amplified. Why? Because machine learning algorithm favors simpler model. When you have two explanations of the world that equally fit the data, you will choose the simplest one. But this means that you will oversimplify the relationship that you learn. Machine learning algorithm minimize average loss. So if your predictions are bad on the minority, as long as you're good on the majority, well, it can still be the model you select. And in some cases, there will be feedback loops in the way you train your algorithm. And for example, ChatGPT now has been trained on, I think, most of the text available on the internet. And it's also being used to produce lots of texts. So if it produces sexist text and it's used to train either ChatGPT or another, or DeepSeek or whatever, you will get reinforcement phenomenon happening. And so when you think about it, there really are lots of different causes for why your algorithm will produce a biased response. And maybe more to the point, there will be different ways we want to address these biases. Depending on the situation, on the problem we are looking, there is no one way to address unfairness in the world. So we want to be able to take this diversity into account. And also, in some cases, we can wonder whether it's the responsibility of the decision maker at that time to, how much of the responsibility of the decision maker at the time it is to address the unfairness in the world and correct the situations and historical discriminations. So, and maybe a last point that I want to discuss before starting to describe how we are going to modelize that from a mathematical perspective is we really have to give up the hope that simply by being blind to a sensitive attribute, a discriminating attribute, to having this blindfold, we're going to be fair. Because even if I remove this sensitive information, I can still guess it using the covariates X that describe the individual. Why? Because, often these covariates are highly correlated with the information that we're trying to remove. For example, your gender will be correlated with your studies. If you give me your name and last name, I can fairly guess your gender sometimes your age, sometimes your social background, sometimes your origin, etc. So really, unfortunately, unawareness of these discriminating factors do not guarantee fairness. Okay? So I will now give you a brief overview of the different techniques that are used to address the problems of algorithmic fairness. And I will do that using the supervised learning formalization, even if it's a bit restrictive. So we assume that we have observations, Zi that are features and Yi that are responses that are drawn IID according to a low P. And now the problem is, given a new feature Z, I want to be able to predict Y. And so I consider a prediction function f, where f of Z will be my prediction for the response Y. And I want this prediction function to be accurate. That is, if I consider a loss function L, I want that the risks, that is the expectation of the loss for predicting f of Z instead of Y, be small. And in the following, I will talk a bit more about regression, so where Y is continuous, and the classical loss is simply the squared loss, so the risk would be the squared risk, the expectation of the square distance between my response and the outcome. But I will also consider some problems of classification, and in this case, we can consider the very classical 0-1 loss, where I lose, my cost is 1 if I make an error in the prediction. And so the risk is the expectation of this indicator. So it's simply the probability of making an error. So far I have not talked about fairness. So to introduce a notion of fairness, I will assume that my feature Z can be decomposed as a pair X and S, where X is a non-sensitive covariate that would give you information. For example, it could be a resume in the recruitment example. And S is a sensitive attribute, which is typically going to be discrete and indicates the group this individual belongs to. And already we can wonder what kind of prediction function are we allowed to consider? Are we allowed to use S at time of prediction? Because we want to be able to do some affirmative action, to treat people differently because they belong to different groups in order to correct existing inequalities. And this would mean that I'm in the awareness framework. So it's when F can depend both on X and S. And in some cases, either I'm not allowed to do that for legal reason, or I don't want to do that for political reason, or simply I don't have access to S at prediction time. And then I must simply rely on X to do my prediction. So this would be the unawareness framework. So because I said that X contains information about S, X and S are not independent, simply being in the unawareness framework does not guarantee fairness, okay? And still we could ask the question, how can we be fair if we don't observe this sensitive attribute S? The thing that I'm hiding here is that I'm going to assume that I have access to a training data set where I observe both X and S. So that's, if I train functions of the form that only depend on X on this training data, but they are fair, I can hope that on the test set, they will still remain fair. And so in the following, I will use Z to denote the argument of my function. So it will be either both X and S if I'm allowed to use S, or simply X. Usually the way fairness is presented is we say that we have two main paradigms. I think the division is not always that clear, but typically we could consider that in some settings, fairness is best defined at the individual level, and that a fair decision is one that treats similar individuals similarly. In the sense, similar individual, of course, if I only consider relevant information. So that means that I ask that my prediction should be regular with a certain metric that only takes into account the relevant information. And this notion is related to concerns on consistency. I want to make consistent decisions, a similar decision in similar situation, and arbitrariness, because I only take into account the relevant information for my decision. But in some cases, you could also say that discrimination is only detected at the group level, and that we should think about fairness at the group level. So this would give you the group fairness approach, which asks that groups of individuals should be treated similarly. And basically, I'm going to look at the distribution, for example, of the outcome or of the risk on the different group and ask that they be the same. So my work is in the group fairness approach, and I will be talking a bit more about this approach. And even in the group fairness paradigm, actually, there are different approaches to defining what a fair decision would be. For example, if you're considering facial recognition, you can say that a decision is fair if it has the same accuracy over all groups. So that would be the risk-based approach. So we require that they are fair. I mean, the risks of the different groups are either the same, so this is the equal risk criteria, or I can also say that if I have a prediction that has the same risk for every group and I manage somehow to improve it on some group without worsening it on others, then I can still do that. And that actually what I want to do is find a prediction that has the lowest risk on the worst group, basically. So this is the min-max fairness criteria. And there are other fairness criteria based on risk. Another approach is to say what we want to model is the influence of the sensitive attribute on the decision, on the outcome. And so we should use causal modeling on this process and ensure that the sensitive attribute S does not influence too much the outcome. Maybe a toy model in this problem, maybe the simplest approach would be that of counterfactual fairness. So here I have a very simple causal graph where X is again my non-sensitive covariate, my resume, for example, and it's influenced both by S, the gender or the origin of the candidate, and U, a non-observed latent variable that would, for example, encode the worthiness of the candidate, how much hardworking he was or she was, etc. And so the idea of counterfactual fairness is to ensure that this individual that is described by S and U would have had the same prediction if she had or he had been in a different group S but had still had the same U. So basically what this approach does is it's building a counterfactual individual. When you have an individual X that arrives, X and S, you build a counterfactual version of what would have happened if this individual had been in the other group, and you ensure that you give the same prediction to both. Okay, so that's an example of causal fairness approach. And finally, the statistical fairness framework says that we don't really care about what's going on within the graph. What we really care about is the outcome of my prediction. And there should be some form of statistical parity across the different groups, just looking at the outcomes. And so this is the criteria that we looked at, the approach that we looked at. And I left what statistical parity meant a bit vague. There actually could be different definitions of what statistical parity means. So just consider the problem of classification and assume you're in a recruitment context. So you have people that are described by resumes, a sensitive attribute that indicates their group, and Y is 1 if they're qualified and 0 otherwise. And in this context of classification, we say that a classifier, G, verifies demographic parity if its prediction is statistically independent of the group. Statistically independent because, of course, if I'm in the awareness framework, Z is both X and S. So I can depend explicitly on S, but I want my prediction to be statistically independent, so distributed equally in the group. And here I have a prediction that is either 0 or 1. So this simply means that the probability of predicting 1, of hiring a candidate, is the same in all groups. And this is related to the notion of quotas, because if the probability of being hired is the same, is independent of the group, you can see that, well, at the end of the day, among the pools of candidates that I will have recruited, the proportion of the group will be the same as in the original pool of candidates. So this is really related to the notion of quotas. On the other hand, there is no notion of Y appearing in this definition. So, and especially the original proportion of good candidates in the different groups could be not equal. And we don't want to be close to the original proportion, to this historical inequality. So this is really a notion that is related to the idea of intervening to mitigate historical inequalities. And an argument against this criteria is that it's not always the fairest choice. There is no notion of, why, no notion of merit. And especially if I just flip a coin and base my hiring process on this, it will be fair according to this criteria of demographic parity, but unfair according to every good science. So if we want to mitigate this and consider a criteria more based on merit, so we can consider the criteria of equal opportunity. And we say that a classifier verifies equal opportunity if the outcome, my prediction, is independent of my group conditionally on the fact that y is equal to 1. So the fact that I hire a candidate conditionally on the fact that this candidate is good is the same in our group. And this is really related to the notion of merit. The problem is now if I'm reproducing data with measurements error or biases in the Y's. For example, the assessment that the candidate was good was made by a manager who was sexist or racist or whatever. I'm going to reproduce these biases. So you cannot have everything. And of course, there is a symmetric version of this, which is called equality of odd, where instead of simply conditioning on y equal 1, I also condition y equal to 0. And you can show that these two criteria are actually incompatible. You cannot have, except in some very, very specific cases where not doing any correction would be fair, you cannot have both criteria. And this criteria that I described for classification can, of course, be extended to regression. Right. So here now we're trying to predict a response Y that is continuous, for example, a salary. And I can extend demographic parity by asking my prediction function to be such that the prediction will be statistically independent of the group. So the distribution of the prediction will be the same in each group, the distribution of the salary, for example. Equality of odds can be extended to the notion of separation. And we say that the prediction function verifies separation if my prediction is statistically independent of S, conditionally on the value of the candidate on Y. So conditionally on Y, I want my distribution, my predictions to be the same in each group. And there is a third criteria in this case of regression, which is sufficiency. And it requires that S and Y are independent conditionally on my prediction. And this is related to the notion of group-wise calibration. Okay. So just as a summary for this introduction, so there is really a diversity of approaches in fairness, of ways of defining what a fair decision would be from a mathematical perspective, which really reflects actually the different notions of fairness that we want to apply in different situations from an ethical point of view. And especially we can consider that fairness should be at the individual or at the group level, that it should be based on criteria of risk or on the causal model or simply on the distribution of the outputs. And of course, we can wonder whether there are any relationship between these approaches. And of course, even if we know that in some setting, this is the good ethical notion of fairness, so this translates into a mathematical approach to this problem, and I have chosen my criteria. There are more practical questions, such as how do I enforce now this criteria? What am I actually doing? Because I'm improving lives for some people, but probably making it worse for others, so I would like to understand what trade-offs are with regard to this problem. What is the cost? Because I'm adding constraint to my prediction, so I'm going to lose in accuracy, probably. And is there a way to do some meaningful relaxation between accuracy and fairness? To convince people to improve things in practice. So this was really the broad angle, and in the remainder of the talk, I will discuss about a very specific problem that we looked at. So the problems of classification and regression in the statistical fairness framework under this demographic parity constraint that asks that the distribution of the prediction was the same for all groups. Okay, and I will start with the awareness framework because it's the one where things are most easy to understand. But actually, I will start with the unconstrained problem, where there are no fairness constraints, and simply consider a problem where I have y that is either 0 or 1, and I have two groups, 1 or 2, and I'm going to denote eta, this conditional expectation of y, given x and s. So because y is either 0 or 1, actually eta is the probability that y is equal to 1. And I can consider this as a classification problem, either considering the 0-1 loss that I told you earlier about. The problem of the 0-1 loss is that it's super symmetrical, and if I'm hiring some people, it does not have the same cost to hire someone that is incompetent or to miss a good candidate, So I want to be able to weigh these two errors differently. And so I'm going to consider a family of risk or tau, where tau is in 0, 1, which is simply tau times the probability of predicting 1 when the answer is 0, plus 1 minus tau times the probability of predicting 0 when the answer is 1. And if I condition on x and y and I reshuffle things a bit, I can see that this is actually equivalent to the expectation of my predictions times tau minus eta. So this formula here, plus some constant. And now if I want to minimize this, well, g is either 0 or 1, so it should be 1 whenever this is negative, and 0 whenever this is positive. So this gives me the base classifier for this problem, which is really the indicator that eta is above the tau. So tau is a weight originally, but it really acts as a threshold, in the sense that if tau is low, and the threshold is low, lots of people will be accepted. And if I increase the threshold for an individual, this individual will be accepted until eta is at the threshold, and then it will be rejected, okay? So we have a behavior that is called nestedness of the rejection regions, or here I call it nestedness of classifiers. So this is for the classification problem. But we can also look at the problem of estimating eta at the regression problem. So here we want to minimize the squared risk. And again, conditioning on S and Y, I can see that it's equivalent to minimizing the expectation of the square distance between my prediction and eta. And well, of course, here the minimizer is simply choosing f to be equal to eta. And so this is nice because here we see that really there is an equivalence between the problem of classification and regression, in the sense that if I can solve my regression problem, if I can estimate this f bias eta, well, I can obtain what's called plug-in classifiers. So if I can estimate the quantity f bias, I obtain a classifier by simply looking at whether my prediction is above the threshold. Okay? But actually, it works also in the other way, in the sense that if I can solve all the classification problem for all threshold tau, I can actually recover my prediction f bias, because I just have to look for an individual when the classifier stops returning 1 and starts returning 0. And I know that at this threshold, well, the threshold is equal to f bias. So I can recover f bias. So this relationship is used to build classifiers. I don't think it's used that much to build a regression function, but it will be interesting if these relationships still hold under some fairness constraints. So that's one of the questions that I'm going to discuss in the following. Okay. So I'm going to start by considering the problem of regression under demographic parity. So these are previous results that were obtained, among other co-authors, by Evgeny. So here we are trying to solve the problem of minimizing the squared risk under this demographic parity constraint that the prediction is statistically independent of the group. And before presenting these results, I have to give you a brief reminder on optimal transport. Just how many of you are not familiar with optimal transport? Oh, wow. Okay, so this will be this will be quick. So you know that optimal transport is a way to define the distances between probability measures. Here I consider two probability measures, mu1 and mu2, and the cost. And the optimal transport distance from mu1 to mu2 with cost t is simply the infimum over all couplings with first marginal given by mu1 and second marginal given by mu2 of the expectation of the cost between the first and the second marginal. So really, we're trying to couple some distributions to send the distribution mu1 to a distribution mu2, and to do it in a cost-efficient manner, with regard to the cost c. And the most famous example is the Wasserstein 2 distance, where the cost is simply the squared distance between 2 points here on the real line. And so if I rewrite the definition, this is the definition. So it's the infimum between couplings between x and y with marginal mu1 and mu2 of the expected distance, square distance between x and y. And actually, this problem is solved by a deterministic function. I can send deterministically x to t of x, and this is called a transport map. And so this problem solution corresponds to the infimum over maps t of the distance between x and t of x squared. And of course, t must verify the constraint that t of x here should have the distribution that y had, so the distribution mu2. So we have this expression here that the push forward measure of mu1 through t is equal to mu2. And the push-forward measure of mu1 through t, so la mesure image de mu1 par t, is really the measure that t of x has when x follows mu1. And so what is nice in this example of Wasserstein distance is that you have the fact that this problem is solved by a deterministic function here, t of x, and that we have an explicit formula for this function written here. So here f is the CDF and f minus 1 is the quantile function. Basically what this expression tells you is that the optimal way to transport mu1 to mu2 is to match quantile, to send the quantile of level epsilon of mu1 to the quantile of level epsilon of mu2. And this is really this expression. So, maybe you're less familiar with the notion of Wasserstein barycenter, but because we are able to define distances between probability measures, we can define barycenters of these probability measures, which will simply be probability measures that minimize P1 times the distance between mu1 and mu, plus P2 times the distance between mu2 and mu, where P1 and P2 are weights are positive and sum to 1. And again, in the Wasserstein barycenter example, we have an explicit formula of this barycenter between the measures mu1 and mu2, here given by this expression. So previously, we were matching the quantile of level epsilon of mu1 and sending it to mu2. Now we are going to match these two quantiles and send them to the same points. And so the quantiles of the original distribution will be sent to their barycenter, so that the quantile of the new barycenter mu is the barycenter of the quantile. The quantile of the barycenter is the barycenter of the quantile. This is really, some nice property of the Wasserstein problem, and it does not hold true in general. And especially in general, you sometimes do not have transport maps. You have probabilistic transport plans. And even when you have transport maps, you don't have necessarily explicit solutions to this problem of barycenter. Okay, so how does this relate to the problem of regression under demographic parity? Well, this constraint, independence of the distribution with regard to the group, can actually be rewritten with this push-forward measure notations. I want that the push-forward measure of this, so mu1 is the distribution of x in group 1, and its push-forward measure through the prediction in group 1 will be the same as the push-forward measure of mu2 through the prediction function for group 2. So if I did not have this constraint, I would simply predict this eta, but these eta have different distributions in both groups, so I must modify them and send them to a new distribution, basically, that will be the same for a group, but I want still that it's close to the original distribution. So that's where the barycenter of the original distributions appear. And so you have a result that was obtained by Evgeny and Gaucher, and at the same time by Rigolet, Loubès, and Lebrick, which showed that really the problem of fair regression is solved by the solution of a barycenter problem between the distribution of these etas, eta, yeah. So the conditional expectation of y in the different group. And so the solution of this problem is given by the solution of the Wasserstein barycenter problem. So this is a bit of a nasty formula, but really basically what it means is you're still matching quantiles. So if you have an individual that arrives, let's say a woman, and you want to give her a salary, you will look at the quantile to which she belongs in our group, rank her within our own peers, and then you will match her with a man of the same quantile in the other group, and we will give them both the same salary. That would be the average of the original salaries. So you still have these matching quantiles, and this has a very nice properties. First, because we are matching quantile. If a woman was better, had a better quantile than another woman, she will have a better salary. Okay, so you're preserving order within groups, basically, with your fairness corrections. There is a nice interpretation of how you're matching women of a given quantiles with men of the same quantiles in their group. Basically, it's as if you were building counterfactual of what this person would have been if she had been in the other group. So you have an interpretation in terms of causal fairness, even if in this case, if you were in the causal fairness, the causal graph would tell you how to match people, and here you're finding a way to match people, but still. And because we have this explicit formula, we can build plugin estimators. I mean, I could have like a black box algorithm that will estimate eta, my conditional expectation of y. And then if I have another sample, I can estimate this CDFs and quantile functions and proportion of the different group, and just use this to build a plugin estimator. So that's for the regression problem. Now for the classification problem. So now we want to minimize this weighted risk, that I said is equal up to a constant to this quantity, under the constraint that the probability of predicting one is the same in a group. And there was a previous result that stated that this problem is solved by a function of the form indicator that the probability that y is equal to 1 is above the threshold tau, plus some correction that will depend on the group. And this correction is lambda tau divided by P1 if you're in group 1, or minus lambda tau divided by P2 if you're in group 2. And lambda tau here is the only parameter, so that this kind of classifier verifies the parity constraint. So this formula is not very explicit. In particular, there is no explicit formula for lambda tau. And it's hard just looking at that to know, for example, if these classifiers are still nested. If you increase the threshold, will you, just reject more people, or will you start accepting other people? Because lambda tau is also going to vary. However, it's quite intuitive that your optimal classifier should be, I accept people with eta above some group-dependent threshold. Because if I can accept 30% of people, I know I can accept 30% of people in each group, and I know that in each group I should choose the best 30% of people. So basically, I know that I should look at a prediction function that rank the people in that group, find their quantile, and look whether this quantile is above some, let's say 0.7 in my example. And actually, what is interesting is that looking at whether some person is above the quantile of level 0.7 in their group is the same as looking at whether their fair prediction is above the quantile of level 0.7 among all fair predictions, because of these matching properties of my fair prediction. So I can really write my optimal classifier as the indicator that the fair prediction is above some value that will correspond here to the quantile of level epsilon. And of course, I have not told you how to choose this value. To choose this value optimally, I have to minimize the risk, but just by writing a prediction this way, I know that the demographic parity constraint will be satisfied. And what we were able to show is that actually the optimal value of the threshold should be tau. So the optimal classifier is obtained by thresholding the optimal fair regression function at the level tau. And we still have this equivalence that we had in the base case without fairness constraints, where there is equivalence between classification and regression. So this has nice implications. For example, because F was preserving this order within group, now G is also preserving this order within group. Because we had this interpretation of F in terms of causal fairness and counterfactual individuals, we also have it now. I can show directly that these classifiers are nested. And if I increase tau, well, I will only reject some more people. And so I told you how to estimate F using plugin classifiers, so I can, plugin of quantities that I estimate, so I can have a plugin classifier. But conversely, I could estimate these classifiers. If I had an estimate of eta, I can find a lambda tau on another data set, so that on this other data set, this classifier is fair. And so I could obtain estimates for these classifiers, and then I could use these estimates to recover F star. So I can build classifiers and use it to recover regression functions. So that's for the awareness case. Now, do these relationships still hold in the unawareness case? It's very close. They are very related. The only thing is now I cannot use S in my prediction at prediction time. So for example, in the classification problem, I'm still minimizing the same risk, except that now my function only depends on X. And I still have these constraints, but now the problem is if I write it in terms of push-forward measure, I want that the push-forward measure of mu1 through G is the same as the push-forward measure of mu2 through G. So virtually, it's as if I had two constraints, on the push-forward measure of mu through two different measures for just one function, g. Okay? So it's harder to construct classifiers that verify this constraint. And there is a nice way to work around this difficulty that is due to a lemma by Nicolas Schroeder and Evgeny. And what they showed is what really matters is the Jordan decomposition of the difference between the measure mu1 and mu2. So again, mu1 is the law of x in group 1, mu2 law of x in group 2. So the Jordan decomposition of measure is a way to write the sign measure mu1 and minus mu2 as the difference between two, so here it's proportional to probability measure mu plus and minus mu minus that have disjoint support. So really mu plus is the excess mass of mu1 and mu minus is the excess mass of mu2, and they have disjoint support. And what Evgeny and Nicolas showed is that demographic parity is verified if and only if it's verified with the pair of measures mu minus and mu plus. So before we had this constraint with regard to mu1 and mu2, and actually it only matters with regard to mu minus and mu plus. And what is nice is because these measures have disjoint support, now virtually I can construct a small function classifier g plus on the support of mu plus, and another classifier g minus on the support of mu minus. And so I'm back to having two functions for two constraints. So my problem becomes easier. And so if I want to solve this problem, now I only have to rewrite the risk in terms of this new probability measure, so do a bit of change in probabilities. And so what we showed is that we obtained an expression for the fair classifier that depends on this function delta of x, which is the probability that x is in group 1 divided by p1 minus the probability that x is in group 2 divided by p2. So delta is very positive and large if you strongly believe that the individual is in group 1, very negative if you strongly believe that it's in group 2, and 0 if you don't really know if it's in group 1 or group 2, basically. And what we showed is that the optimal classifier can be written as the indicator that eta is above the threshold plus a correction that is now delta times lambda tau. And lambda tau is again the constraint, the parameter such that the demographic parity constraint for this classifier is verified. And if we want to compare it to what we had in the awareness case, in the awareness case, we had this correction, so indicator of being in group 1 divided by P1 minus indicator of being in group 2 divided by P2. And here we don't know this indicator, we don't observe S, so these are virtually replaced by the probabilities of being in the two groups. So this characterization recovers the one that we had in the awareness as a special case if S is measurable with regard to X. Okay. But I have the same criticism that I had with the previous expression, which is it's not obvious that this expression is nested, for example. And yet I can recover I can estimate some classifiers if I can estimate eta and delta, so the probability of being in the different group on a first data set, and then I can find lambda, sorry here, I can have an estimate for this classifiers. Okay, great. What we can say also is that we can show that under my assumptions, this classifier does not preserve ordering within a group. So you could have people in a discriminated group that after fairness correction will be even worse off. As I said, you can obtain plugin classifiers if you estimate eta and delta. And another remark is that in practice, I think that what most people do, because this problem of unawareness is actually very common when you don't have access to S, is that they estimate this unobserved variable instead of using the probabilities that it's in the different group. So this would be the optimal way of obtaining, the way of obtaining the optimal classifiers instead of simply replacing S by its estimate. Okay. And so we also looked at the problem of regression on our regression. So now we want to minimize the squared risk, again under the demographic parity constraint, and again using this decomposition of Jordan and the same trick of changing the risk in terms of mu plus and mu minus, we were able to show that this problem is, the solution to this problem is given by the solution of, again, an optimal, a barycenter problem between mu plus and mu minus with optimal transport costs that are now a bit different than what we had before. Before we only had the square distance between eta and x. Now it also depends on the absolute value of delta. So we have this cost now. We were able to show that the optimal prediction function is deterministic. But the problem is that this kind of optimal transport problem here, so the transport cost depends on two quantities, basically on eta and on delta. And I'm going to, send the points that is described by this eta and delta to one prediction y. So it's a problem of sending a quantity that is basically in 2 dimensions to a quantity in 1 dimension. So it's called a multi-to-one dimensional transport problem. And this transport problem have not been studied so much. And especially there is no explicit solutions for the barycenter of this problem. So we have no explicit solution for the optimal solution S star. So we could approximate the solution on a discrete grid using optimal transport solvers, but we don't have an explicit solution to just plug in quantities that we have estimated before. And so we could ask the question of, do we still have the relationship between classification and regression? Because if we had this equivalence, because I know how to build my classifiers, I could have another way of estimating this regression function by using the classifier that I have built for the different risk levels. So do we still have this formula? Can we write the optimal classifier as the indicator that the optimal regression function is above the threshold tau, which again, if I can solve for every tau, would allow me to estimate the threshold tau at which the classifier changes value and so recover my fair regression function. And the problem is, so this was the formula for the optimal classifiers. And if I represent the situation on the 2D plan with here delta and here eta, and the measures mu plus and mu minus, I know that my classifier will have these types of decision frontier, which will be a straight line, which goes through tau at delta equals 0. So if delta is 0 and I don't know if the person is in group 1 or 2, I'm not going to correct the prediction. And the slope of this straight line is given by lambda tau, which is the parameter such that this constraint is verified. So basically the mass here is the same as the mass here, okay? And now depending on which side of the frontier you're on, you will either have a prediction 1 or 0. And the problem, if I consider the prediction at another value of tau, let's say tau prime, I will change my slope, and there is no guarantee that these slopes will not intersect. So basically, there is no guarantee that my classifier is nested. And actually, we were able to show that there are some problems where the classification problem is nested, and there are some problems where it's not actually. And so what's going on when the classification problem is not nested is that you can have a very low threshold where you admitted almost everyone but rejecting some people. And when you increase the threshold, you reject some more people, but some people that were rejected before get admitted. And this is the optimal decision. So it's very counterintuitive. And of course, you see that when you're not nested, you cannot have this kind of expression. Because this would mean that if I increase tau, I'm only going to reject more people, so that's my problem is nested. And what we were able to show is that this nestedness assumption is actually minimalist, minimal in some sense, in the sense that if my classifiers are nested, then I have this equivalence. And if my classifiers are not nested, then there exists a threshold such that this type of classifier will be suboptimal in terms of risk. So as a conclusion, so I presented you 2 frameworks that are apparently very close to one another. And in the awareness framework, we have very nice properties where we have explicit formulas for classification and regression under fairness constraints you can actually show that these problems are equivalent, that these predictions preserve ordering within group, and that the classifier that you can build are nested. And simply when you cannot use S at prediction time, the situation changes drastically. You don't have always equivalence between regression and classification. we were still able to show that you have a deterministic prediction function, optimal regression function that is the solution of a barycenter problem. But now there are some very complex costs and we have no explicit solution for this problem. In the unawareness framework, our predictions do not preserve ordering within group, and the classifiers are not always nested, which means that you can have very weird phenomena where you raise the bar and you start admitting people that were rejected before. Okay, do you have questions?
Yeah, one or two short questions.
I was just wondering, the conclusion out of it would be that unawareness framework is not very good.
I think the conclusion should be, if you want to do this kind of criteria, you should try to be in the awareness framework. But the conclusion is also, I mean, that's good if you're a decision maker and you want to allow people to use S. But in some cases, you will not. I mean, you don't have any choice and you don't have access to S. So I mean, it would be more about the problems of unawareness and what should be aware of if you're trying to do fairness in this problem.
Did you?
So first, I want to thank you for the talk. It was very nice, and also I like the conclusion that if you want to be fair with respect to an attribute, then you should, let's say, be aware, or you should not ignore that attribute. That it's better to know one's biases before taking a decision. So I had just a question. So do you have you said you also had examples where actually it is nested. Do you have a kind of I don't know, sufficient condition that you could say, well, if this is satisfied, then it would be nested, and generic condition?
No, we don't. It's even hard to know if in practice most of the problems are nested or are not nested. So we don't have any intuition on that.
Okay, so you can just exhibit examples where it's the case or not. But,
And another thing is it can be not nested on a small portion of the space and nested everywhere else. So.
Thank you, Solenne, again. And